Okay, hello everyone. The whole point of this video here is to try and explain to you what is QAM or QPSK. This here is a way of reusing mathematics, especially by using our wave mathematics that we will have learnt when we're younger. Now, or even if you're listening to this and you're at a certain age. Now, what I want to try and say here, if you're 16, you should be able to understand this. You can understand this. You've got to believe you can understand this. It's not as difficult as what you think it is. Okay, there's a lot of people who are out there and they don't understand what the maths is. When they look at it at the end, if you just take it through step by step, then we will all understand this together. However, I'm going to need you to put your lovely thinking cap on. As you can see, I'm more of an engineer and maths user rather than an arty person. So this is our thinking cap. Okay, and enjoy. I hope this will be very informative to you. Okay, so first of all, let's get rid of all this. Now, first of all, we're going to talk about waves. Now, I'm not specifically going on about surfing here, but I'm trying to remind you of how we represent waves mathematically. What do they actually mean? Okay, so what we're going to do first. What does a cos wave look like? Anyone remember what this cos of theta looks like? Anyone remember? Well, in case you're not sure, I'm going to tell you the answer anyway. Cos of theta. If this is our naught, this is our 1, minus 1, it will look something like a bucket shape here. Okay, and anyone remember our sine of theta? Anyone out there? Okay, yeah, you've got it. It looks like this. This is our sine of theta. We've got this is our naught, that's our 1, and that's our minus 1 down there. Okay, so now, what is minus cos and minus sine? How do we represent those? Well, our minus cos, it's easy, we just invert it. All this stuff you can go back and you can look at your GCSE books or whatever equivalent it is wherever you are in the world watching this. Minus cos, it's easy, we just invert the cos wave. And what's our minus sine? Yep, you've got it. All we do is we invert our sine wave. Not drawing the most accurately there. Like I said, I'm an artist, not a... I'm not an artist. I'm a maths user and engineer. And also I'd like to think of myself as a bit as a scientist. But I'm more of an engineer. Okay, there's our waves for you. So, this here is fundamental to understanding QAM, or quadrature amplitude modulation. And all this will come to in a second. But now I'm going to come away from this. And instead now I'm going to talk to you about binary numbers. Okay, so all this here, I want you to try and take a note down for you. Okay, try and note this down and record everything that I'm saying. And I'm not the type of person to give you notes. Instead, you should be understanding, you should be listening and taking notes of everything and write them down how you need to. If you're not sure about this, pause, and there will be plenty of other information on the internet. In fact, even one of my other videos should be showing this, which I'll be putting up on the internet very soon. Okay, so now let's change tactic and go to something very different. We're going to talk about binary numbers. Yeah, if you're 16, you should be able to have done this as well. So if you had your birthday cake, and if you had your 16 candles on it, then everything should be fine. And you should be able to understand this as well. So, let's do in separate colours, it's easier. So if I've got my decimal numbers here, decimal, that's where it's 0 all the way to 10. Sorry, all the way to 9, we even call it. But if we've got our binary numbers, it's all the way from 0 all the way to 1. But there's only 2, hence binary, bi means 2. So, I'm now going to draw here my decimal numbers. So I'm going to go 0, 1, 2, and 3. Let's just get rid of this. And now here, I'm just going to put different columns. Here I'm going to put my binary numbers. And this here we're going to call the most significant bit. Okay? And here we're going to call it the least significant bit. Maybe this will all come back to you as I'm writing this. So I'm going to do this in different colours actually. Let me just go back. Here, helps to have different colours. Let's use our red. Okay. Just to stop confusing you, let's get rid of that. Remember, you should be recording this down. You should be understanding it and writing in your own way. This is very important. So here, I'm going to put a 0. And here, I'm going to put a 0. Okay, I'm just going to underline this. So, what is 1 in terms of binary? It's where the most significant bit, so this is your equivalent of your tens in decimal, would be 0. But your least significant bit now is equal to 1. I'll be doing another video to understand binary numbers a bit better, okay, if you're not following this. Next number along, most significant bit now changes, but our least significant bit, our next column, changes back to 0. And finally, if you remember, our 3 would now be 2 1s. This here is where there are 2 bits. We have our most significant bit and our least significant bit. There are 2 of them here. Something quite important to remember as well. Now, what's so important about this? I'm going to hopefully very quickly draw these sine waves because I'd rather not do them quickly. I'd rather not mess them up. So just give me 1 second. Here I'm going to draw my cos of theta. Here I'm going to draw my minus cos of theta. Here I'm going to draw my sine of theta. And here I'm going to draw my minus sine of theta. Okay, so let's just start with our minus sine. So what I'm actually going to do here, so I'm just going to zoom in here so you get a better idea. Okay. Should focus, please. Please focus. Oh, looking a bit better. There we go. Nice camera this is as well. I like it. So if you can see the numbers along here, this is our theta, this is our amplitude up here. Okay. Let's move a little bit further back. Okay. Now, along here, along the bottom, which you should be able to see, is that I've got the numbers 0 going all the way up to 360 with 45 gaps. This is very important. If you try and remember from school, this should be quite easy for you to follow. Okay? What matters is that they are spaced out correctly. So our sine wave, we know it starts at 0, maximum is at 90, at 180 it goes back to 0, at 270 it goes down, and then, if you look, I've already done a mistake there, because this is meant to be my minus sine that I'm drawing here. Okay, now let's avoid that mistake there. This is my minus sine wave there. Now, if you get the idea, I'm just going to quickly draw out the others while I'm here. This here, there's plenty of other information on the internet. So my sine wave, I'm just going to quickly do this here, as I'd rather do everything in one take. Now I'm going to draw my cos waves. It starts at 1, at 90 we're at 0, at 180 we're at minus 1, at 270 we're at 0, and 360 we're all the way back up again. Okay, sorry, there you go, I've already done a mistake. Again. This is what happens when you do things in reverse order. See, anyone can make mistakes, even me. And then, if we're going to go up here, now I've got my cos wave. Okay? Now I've got my cos, minus cos, sine, and minus sine. Why are these important? Why have I drawn these out so neatly here? Well, I'll explain. We're going to go back to our binary numbers. I'm going to call now, this is equal to 0. Sorry. I've used the wrong colour here. Let's not confuse you. Okay, we've got our binary numbers out again. 1, 2, 0, 1, 2, 3. Now, what I'm going to have here is so our most significant bit, which was in red, we now have 0, 0, 1, 1. And our least significant bit is 0, 1, 1, whoop, 0, 1. So now I want to say that whenever we have a most significant bit, so this is in red, whenever I've got that equal to 0, I'm going to use a cos wave, just a normal cos wave. This here is equal to 0. Now if I've got my minus cos wave, I'm going to invert it. 1 inverted, 0 inverted makes 1. So now I'm going to call my minus cos wave a 1. Similar idea for the sine wave. I'm going to call this 0, and I'm going to call this one 1. So whenever in our binary numbers here, whenever in our table, our binary number table here, whenever we see, let's go with this, whenever we see a most significant 0, I want you to think about cos wave. If it's a 1, I want you to think about minus cos wave. When I'm on about a least significant bit, 0, I'm on about a sine wave. And when I see a 1, I'm on about a minus sine wave. This is something that you've got to think. So this one here makes this. This one here makes this. Try and think that they are always corresponding in this way. Very important. Now, what's the trick? We now have to add the waves. Add them. Okay, now you're getting a bit complicated about this. What's he going on about? Let's start at number 2 here. So number 2, you can see it's 1 and 0. So let's just get rid of everything else here. Just make sure that you shouldn't look that back. If you've missed that out, don't be afraid to rewind and go back. So I've got my 2, I've got my 1 and my 0. So let's just tie that up a bit even more. So what did I say before? What is a red most significant bit? What does it look like? If you remember, we're on about a minus cos wave. Oh, sorry, let's change the colour. We're on about a minus cos of theta. And what is our naught? What's just our naught for the green, for the least significant bit? Well, we're on about a sine wave, sine of theta. We all remember? If you're not sure, go back, rewind several seconds, and then you can see our 1 is equal to a minus cos wave, and our 0 is equal to a sine wave. Now I'm just going to draw these out quickly here, so we get a better understanding. So if you remember, okay, minus cos wave looks like this. This is our minus cos wave. This mountain shape, upside down bucket. And our sine wave, it looks like this. And this is our sine wave. Okay, so now we've got 1, and here we've got 0. Okay, so you probably think I've gone around the houses and I've redrawn everything, but I want you to try and understand this. But now I'm going to add these together, and this is going to equal this, what I'm about to draw. Okay, so what's the simplest way of doing it? Yeah, sure, you can use a mathematical function. Use Excel sheets. Excel sheets are awesome for this type of thing. They'll give you a very, very, very accurate way of doing it. But we're just going to go through the theory here. So, I can do this quite simply. So here, I'm going to look at where theta is 0. I've got 0 and I've got minus 1. So I'm going to make a point here. Okay, in fact, let's zoom in on this. Okay. Okay, so I'm actually going to draw the bottom one to make life easier. I'll zoom out in a minute and then you'll follow what I'm saying. So I've got 0 and minus 1, this is here. At my 90, if you look back, and you should have taken notes, at my 90 I've got 1 and I've got 0, so I'm already going up here. At my 180, I've got 0 and I've got 1. So now we're going up here. At my 270, I've got -1 and I've got 0. So it's going down here. And then at our 360, I've got 0 and -1. Okay, so let's go out here. If you follow, if you add these all together, then you'll see these points here. Well, I can already tell you that my wave looks something like this. Okay, now if you really want to do the maths, I can tell you that this here is the square root of 2. But we're not going to worry about that now. This will be in another class. All I want you to see is that this has become a different wave. We now have a different shaped wave that makes this here equal to number 2. This here makes 2. So now whenever we see the number 2, we know that we're looking at this shape here. Number 2 makes this shape. So what happens if I added a different shape? What happens if I instead, so I wasn't looking at number 2. Let's say I was looking at number 3 instead. It's number 3. That's going to be a 1. And that's going to be a 1 as well. Go back if you're not following what this is. Okay, you can always go backwards. Okay. Always turn your phones off when lectures are on. Perfect example. Go to university if you do, turn your phone off. Or at least put it on silent. Okay, now I'm going to reuse some of this here. Okay, so now I've got my 3, I've got my most significant bit, which is still my 1. But this time I've got a 1 here and I had a 0. So I want to change this around here. So this one here, I actually want to have a minus sine of theta, which would make this a 1. And then, so what I'm going to do here, I'm going to draw my minus sine wave, which if you followed a second ago, then you should understand how we draw this. So this is my minus sine wave. Now, I'm going to use the same technique and just do it quickly. So if you don't follow how I'm doing it this time, go back and then you'll see it again. So this time here, I want this to be representing my 3. So I'm just going to do this quickly here. So I've got my 0 and I've got my -1. I've got my 0. I've got my minus 90. 1. 1 there. Got my 0 and I've got my 1. So what's this one look like instead? This here. We've got a wave looking like this instead. Which actually, sorry. One there should be looking a bit different. Okay, and it should be looking more like that. Okay. What's this trying to show? We now have 2 different waves, which are looking different. So this wave here describes our number 3. This wave here describes our number 2. What's this all for? What I want you to take note of is the peak here, which is 135. And this peak here is 225. This is going to be very important. All this type of mass, where you can find it, this here is a bit deeper than where I want to go today. But right now, just think the peak of 2 is 135 and the peak of 3 is 225. As you can see, we're doing a lot of corresponding here. This is what matters. Okay? So now, what's a different way of representing this? Well, now we're going to go to something else, which you might have to remember from when you're younger. And we're going to go on to polar graphs. Polar graphs. What do these mean? Well, instead of having where we have theta versus our amplitude, instead we focus more on our differences here. So I'm going to do an example here. I've got my, let's see, we're going to this point here. So I have my angle, which I'm going to call alpha. Okay, and then I've got my point up here. And this here, this line here, is my amplitude. In fact, let's call that theta and we'll stop getting us confused there. So this is how I'd represent it in this way. Okay, this is a polar graph. So what am I going to do? I'm going to take these waves here and I'm going to represent them on my polar graph instead. So now, I'm going to take my value of 2. Okay? I'm going to take my value of 2 here. So let's put this up here. Okay, I know it's 135, so this here is 0 degrees. This here is going up to 90 degrees. This here 180. This is 270 degrees. So what is it? We'll go around to 135. So this here, we have our theta going down to 135. This is number 2. So now we've got number 3. Where's that going to be? That's 225. I can tell that it's going to be over here. And also I can tell the amplitude should be the same as well. So this now is going to be number 3 over here. And I can also tell you that over here, this is going to be a number 1 if you did all the maths. And this is here is going to be a number 0 if you did all the maths. So now we have 4 different graphs. Okay, so here I've only drawn 2. Okay, so let's actually get rid of these to stop confusion. Okay, so I've got my 135 going around there, and I've got my 225 going all the way around there. And now they're being represented, 2 different waves, representing 2 different points. Now let's write out the binary numbers instead for this. Okay, so here we have 1, 0. And here we have our 1 and our 1. So now we have 4 different points that will be represented because they have different angles, because we have 4 different waveforms. And now we'll have different number of bits to represent our number of waveforms. So remember, each number, each binary number makes 2 bits, is represented by 2 bits in this. Each one of those corresponds to one of these black waves, which then can be represented on a polar graph by measuring points. So let's just tidy this up here. Okay, let's get rid of that. Okay, I'm going to just tidy this up a bit more so you focus on it. All of this will be going into further detail later on. So actually, over here, we now have 4 different points. Okay, so I don't know why I got rid of that. This just means in my degrees. We now have 4 different points representing our 4 numbers. And so this is the key to it. From our QPSK, from our QAM, our quadrature, 4 parts, amplitude modulation, quadrature, that is the key to this. We now have, let's just turn that around. This here is called 4 QAM. There are 4 mapping points, is what we call them. 4 mapping points, 4 different graphs. 4 QAM is made up of 2 bits. Okay, now maybe some of you out there have heard of 16 QAM. Anyone heard of 16 QAM? Well, it's easy. Now you understand this. Now you've got this. So 4 QAM, 4 different graphs, 2 bits. 16 QAM, so numbers 0 to 16 in binary. How do you make that? If I was going to go 0, 1, 2, 3, 4, 5, 6, and go all the way down to 16. If I was going to represent that in binary, I would need 4 different bits. So I would have to start from here. 0, 1, 0, 0, 1, 0. 0, 0, 1, 1, until gradually we go down and get to 16, where we have 4 bits. 16 QAM is represented by 4 bits. Easy way to remember this, let's just go down here. If we have 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, okay. What is 2 to the power of 1? 2. What's 2 to the power of 2? 4. What's 3 to the power of 2? 8. What's 4 to the power of 2? Or 2 to the power of 4? 16. 16 bits, or 16 QAM, is represented by 4 bits. It all coincides together. So what you're always doing here, you're just culminating all these little tiny bits of mass that you've been using throughout the years. 16 mapping points. 16 mapping points, 4 bits. What does this look like? Let's tidy everything else up here. Let's get rid of all that. So we now are 4 QAM. Looks like this. So what does our 16 QAM look like? You've got it. 16 mapping points. And there you go. Each one of these points here is represented by a different amplitude and by a different and a different phase. Okay, so it's a different theta and a different amplitude. And each one of these is represented by what would be a different graph. Each mapping point makes a different graph, makes a different waveform. And that's it. And the other thing to point out, 4 QAM was also mean QPSK. Okay, so it means the same thing. Okay. Going out of it there. Okay, so our 4 QAM is also equal to our QPSK. And all to say as well is just to say, this is quite complicated. This is quite complicated to engineer, is 16 QAM. At least several years ago. But nowadays, we can get 32 QAM, which isn't very common. We can get 64 QAM, which is a lot more common. We can get 256 QAM. And nowadays, we can get 4,096 QAM. In what context do I mean? Used in digital video broadcasting, which is a complete other subject. And if you really want to know, 4,096 QAM is used for cable 2. So this is cable. Okay, this is used, will be used, it's just started being used on this date in Germany. It's just being launched around about now. So, there you go. This is the basics of QAM. Now, obviously, if you've got any comments, if there's some things you don't understand, please, please, please ask me and put it down on the comments on YouTube or send me an email at robertjohnwebber at googlemail.com. Okay, send me an email there or watch the video again, whichever you want. If there's things you don't understand, please, please, please let me know and I will do another video or I'll send you a description of a more better way about how to do this. Thank you for the time. Just to let you know, this is my second ever video that I am putting up on YouTube as a lecture. Okay, video 2. So, for my own sake as well, I'd really appreciate it if you did give me this feedback. So, thank you very much for your time. I hope this has been useful to you, and good luck for whatever you are learning QAM for. Thank you.